Guess what the next unit's all about? Ah, so good. Yeah, probability. Um, Generally speaking, probability is a topic that uh, people love or hate. It's a bit of a Marmite topic. I can assure you, for those of you who are going, oh, yeah, the main thing I hate about probability is about how easy it is. This is not an easy unit of work. To be more precise, if you want to give your summary book a heading, put on it probability and then the word distributions. Probability distributions is what we're doing more or less throughout the next few weeks. Okay, so probability distributions, but let's go back a second and say probability. What do you know about probability? Throw out some key terms about probability, things that you remember. This is an awkward start, isn't it? What's the basic definition of probability? Chance is another word. I tend to use chance is the description of what's happening. You're looking at chance, and probability is the mathematical calculation of chance. Do you like that? So chance is like, oh, what are the chances? Like that. Like when I was looking at my footy tipping record for the weekend, I'm thinking, not good. Um, Whereas when you say what is the probability, you're almost going from that informal, subjective, what are the chances, to putting numbers to it. So how do we work out fundamentally, how do we work out a probability? Go on. Yep. No. Tian said something about multiplication. I'd say it's more aligned to division than multiplication, really, the basic definition of probability. I can see that you guys want to be spoon fed. So are you ready to be spoon fed? Here you go. Nom, 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 nom. Recall this stuff. Write it down if you want to, but only if you feel like there are things here that you have forgotten. And based upon my classroom discussion of 1 minute, where all I got was this, like the test pattern, I think perhaps we should go through it a bit. So here's a key concept: sample space. Sample space is where somehow you gather together all the possible outcomes for a particular event happening. Oh, there's a key word as well: event. So probability is all about calculating a numerical percentage or fraction to describe the likelihood of an event happening or not. Does that sound fairly reasonable? It's calculating the likelihood as opposed to subjectively just saying, oh, not good. What are the chances? Not good. Even 50-50 doesn't tend to be really objective, does it? It seems to be quite a subjective thing to say. So the actual listing of those items are what you describe as a sample space. What we've done over the last number of years, from high school to grade 11, is we have worked out different ways of expressing that sample space so that we can efficiently create a sample space. So the least efficient method, but fine for basic ideas, is just to list them, write them all out. And P.S., the sample space is a set. Now that we've done that function studies unit where we talked about set notation with squiggly brackets, or braces is what they're really called, when you write a list out, technically you should write them in braces to say this is the set. Okay, so curly brace bracket, and then if it was what are the outcomes of rolling a six-sided die, it'd be 1, 2, 3, 4, 5, 6 with commas and close the curly brackets. So the set has 6 items in it. Table, like a two-way table, for example. Rolling a die and flipping a coin. The columns are 1 to 6, the rows are head, tail, and then you fill out the table. A nice, efficient way of getting outcomes from 2 disparate events. Carnomat, do you remember those? Like truth things where you say, where you put down the probabilities of A and B and A and not B, etc., etc. A tree diagram, Yes, kind of rings a bell. And starting with W, what's the sort of the more sophisticated tree diagram? A something tree diagram. Who said that? Yeah, weighted. Thanks, Charlie. So weighted tree diagram, when you put the probabilities of each discrete outcome. So rather, like if it was, a spinner with three reds, a blue, and a green on it, you wouldn't go red, red, red on your tree. You'd just go red and put a probability of 3/5 on the branch, and then blue and then green with 1/5, 1/5. So the weighting is the fraction or the probability or the decimal, whatever it happens to be. And a Venn diagram, which is an example one, is down here for two events. You can have three event diagrams. You can have four, but they're a bit tedious. All good? Okay, here's some more concepts back here. So the probability of an event happening is really roughly worked out as by determining the number of matches in the sample set that match event A, and then dividing it by the total number of outcomes. So if the event was for rolling a six-sided die that it's an even number, then there are three ways of getting an even number. So the number of matches is 3, and the sample space size would be 6, so it would be 3/6 or a half. And then we've got our probability arithmetic that I just wanted to remind you of. The probability of A, anyone remember what that one's called? Good. Well done, Shagos. A intersect B is equal to the probability of A multiplied by the probability of B if they are independent. Okay, in other words, A does not affect B and B does not affect A, then we can just multiply the probabilities together. If they are not independent, if they are dependent, then you cannot do that. A intersect B on the Venn diagram is this little middle bit here. It's the bit that both A and B have in common, whether they're independent or not. That's what it is. The probability of A, well done, Monty, union B. The probability of A union B, which means join A and B together, you'd have the probability of A plus the probability of B minus the probability of A intersect B. So in other words, on the Venn diagram, probability of A union B is the whole kit and caboodle. The only thing that would be missing would be any probabilities are outside here. Now, I've got a question mark here, mutually exclusive question mark. What happens to the probability of A intersect B if they're mutually exclusive? 0, good. Who said it over this side? Tian, well done. Yeah, they're 0. I haven't represented this here. If I did, I'd just have nothing here, but really I'd have A as a circle and B as a circle with no overlap. So the probability of A intersect B would be 0. So if they're mutually exclusive, then it means that the probability of A union B would just be the probability of A plus the probability of B, and then none of that stuff there, if they're mutually exclusive. There's nothing overlapping. And this we're going to come back to. I'm putting it there as a PS, but just to remind you that that symbol there, that vertical bar, means the probability of A given B. Okay, what's the probability of A given B? And that's the calculation we do. But the understanding of A given B is that we reduce our sample set by whatever's in B, and then we work out what's left of A. So if I said, what is the probability of everyone's okay, this is going to be a dumb probability. If I said, what is the probability of a student that I select being in year 10, the probability would be 1 in 10, right? Tian. That'd be 1 in 10. But if I said, what is the probability of, what is the probability of, this is going to be dumb. What is the probability of selecting a year 10 student given that they're in year 12, which is the rest of you, aren't you? I think. Oh, hang on. You two are in year 11? You're in year 11? Oh, it's even better then. So if I said, what is the probability of being in year 11 given that the students are not in year 10? It's a bit complicated, but anyway, if I did that, then it wouldn't be 3 in 10, it'd be 3 in 9 because Tian wouldn't stand up to start with. I'm restricting the group to people who are not in year 10. That's what conditional probability is. Don't worry, we'll cover it again a little bit as we move on. All right, any questions on that? Cool. Okay, let's move on. Just recall is all I want because the actual new stuff is over here. And I'm going to do the first task together as a group, and then I'm going to get you to do the second task there on slide 7. So the first task, I'll zoom up just so you can see it, is write out the sample space for flipping 3 coins. And I've asked, how can we do it in an orderly fashion? You know, with efficiency rather than just going, well, it could be head, head, tail. It could be tail, tail, tail. I mean, you could get through them all that way, but it's quite inefficient. Would anyone like? I've got a way in mind. I'm not going to lie. I've got a way in mind for a particular reason, but I wonder if you can guess what I'm thinking. What the most efficient way of doing it would be. Anyone want to have a stab at it? Don't care if you get it wrong. Just care about contributions. How would you do it, Tian? Yep. Oh, kind of like a tree diagram. Yeah, I don't mind that. I'm not going to do it that way because I've got a reason in mind. That doesn't invalidate what you just said. I don't mind that at all. That's a reasonable way of doing it, for sure. Although I have to say that for 3 coins, we might start getting a pretty messy or giant tree diagram as a result. That may be the only negative there. But yeah, a pretty reasonable, efficient way of doing it. If I was going to, I'll be a bit more precise that if I was just going to list them, which is what I'm about to do, is there an efficient way I could list them? Yeah, okay. Cool. Um, sorry. Um, it it does in a way. When listing the outcomes, order does matter, but it's then what I do with those outcomes is where I can decide whether order matters or not. Yeah. What I mean by that is the event might be how likely it is that I get 3 heads. And it doesn't matter whether it's the first 3, the last 3, or a hair. Oh, sorry, I got 3 to start with. What's probably getting 2 heads, whether it's a head head or a head tail head or a head head tail, doesn't matter, right? It's still 2 heads. Whereas what is the probability of getting a head, and a tail? It does matter. So that's all based upon what event I'm looking for. But either way, whether order matters or not, I still have to write down every single possibility. So you can't just say, how do I get 2 heads and a tail? 2 heads and a tail. That's not it. It's actually broken down into more things. Okay, so this is how you can do it. Start off with 3 heads. Then swap a head out for a tail. So that's one. Then have head, head, tail like so. What I'm going to do there is I'm going to move that tail all the way through the list. So the tail is there at the end. Next, I can put it in the middle. And next, I can put it at the start. Okay? Then I'm going to start with a head again, but this time have 2 tails. And now I can move the head through the tails. So tail, head, tail, 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 head. So I've got 3 heads, I've got 2 heads, I've got 1 head, and now I'm going to do no heads. So that's kind of an efficient way of trying to organize your list. Okay, by considering it from the perspective of one of the outcomes, in this case head, and then moving through the list like so. Can you please do the same thing? We've got more to do after this, but can you please do the same thing for 4 coins? So you can start off with head, 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 and then keep going until you get to tail, 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 tail. Okay, if you're watching this on the video, I hope you paused and did the 4 coins, and this is what we would get. A little bit more disorganized than I was hoping for. So we've got 4 heads, we've got 3 heads, we've got 2 heads, we've got 1 head, and then we've got 0 heads here. So we've focused our thinking on the number of heads that were present in our coin toss. Now, let's have a look at the number of outcomes for this. There is one way of getting 3 heads. There is 3 ways of getting 2 heads. There are 3 ways of getting 1 head, and there's 1 way of getting no heads. For 4 heads, there is 1 way of getting 4 heads. There are 4 ways of getting 3 heads. There are 6 ways of getting 2 heads. There is 4 ways of getting 1 head, and there is 1 way of getting 4 tails. Have a look at those numbers there. For 3 heads, the numbers are 1, 3, 3, 1. And for 4 coins, sorry, not heads, coins, I've got 1, 4, 6, 4, 1. Did I not write the 4 in? Someone said it. Who said it down there? Sunny, Pascal's triangle, good. So this kind of distribution of outcomes is what we call a binomial distribution. Binomial meaning 2 possibilities. They are heads and tails in this instance. And as you can see, the number of coins that I flipped directly corresponds to a line on Pascal's triangle. So there's a definite linkage between Pascal's triangle, what happens there, and what's happening in our probability distributions. That is an aside that we're going to come back to a fair bit later on. Here, I'm just going to zoom up so just to focus you on the material here. Here, I'm going to introduce a concept, and I'm going to start by setting up a big capital X. That's an uppercase X. Very important you use an uppercase X for reasons that will become clear later, I hope. So that is really important in mathematics. It's a precision sport. If I say uppercase X, I expect you to use it. It is different from lowercase x. So let X be the number of heads in the sample space of 4 coin flips. So what we're doing is, although there are 2 outcomes, we're really focusing on one of them. And we are viewing our outcomes through that lens. Our lens is, I'm interested in the number of heads. Now, because this is a binomial distribution, not head means tail, so that's fine anyway. But the important thing is I'm focusing on that particular thing, one thing. I'm laser focused on that, and that is the number of heads in the sample space. Then the number of heads flipped gives us a new kind of sample space. It's the number of heads that could be flipped. And X would be the set 0, 1, 2, 3, or 4. 0 heads are flipped, 1 head is flipped, 2, 3, or 4 heads are flipped. Am I making sense so far? Is there any number I've missed out? Is it possible to flip 5 heads on 4 coins? Nope. Is it possible to flip -1? Nope. What about 2.3? Nope. So these 5 possibilities are the only possibilities based on the number of heads that were flipped. I'll zoom out now and I'll talk to it. So this is your key new word for this year, random variable. X is called a random variable. Oops, I don't want to draw in red. Okay, and this is where my language gets a little bit rubbery in an attempt to keep the words simple. When you assign a value to each outcome in the sample set, now the sample set was all 24 possibilities there, and relating it back to what Tian asked before, what we're saying is we're collecting those outcomes together to describe the circumstance. So this sample set here is all the specific, unique outcomes where order effectively does matter when listing them. Okay, these are all the possibilities, or these ones here for 4 coins. But we're grouping these together and we're saying, well, what I'll do is I will use the number 4 to denote how many ways I can get 4 coins. I will use 3 to denote how many ways I can get 3 coins out of 4. So 3 heads, sorry. I will denote 2 to say how many ways I can get 2 heads from 4 coins, and then 1 will be 1 head, and then 0 would mean no heads, all tails, in other words. Okay, so we've assigned a value. 0, 1, 2, 3, 4 are the values that we are assigning. So what we can then say is that, e.g., x equals 2 has 6 ways that it can be getting x equals 2 can be done in 6 different ways, is what I'm trying to say. Okay, so we are assigning a numerical value 0, 1, 2, 3, 4 to describe the sample space of flipping 4 coins. And so if we talked about what happens when x equals 2, the answer would be there are 6 ways that x could equal 2. We're more interested in the probability than the ways, but we'll get to that in a second. Okay, so slide 11 there says there are 2 types of random variables. Let's have a look at that. Number 1, discrete. So whenever you see the word discrete in mathematics, and it's spelt that way, discrete, it means countable or separate, I suppose. The other spelling of discrete, discreet, means that, you know, if I told you a secret, you wouldn't tell anyone else because you're being discreet. Okay, this spelling of discrete means countable or separate. So let's put that down. Countable number of values. The values themselves don't need to be whole numbers. Okay, maybe I won't write this next bit down, but I'll just say it and feel free to annotate your own work if you need to. So, for example, flipping 4 coins is an example, and sorry, this here, x equals 0, 1, 2, 3, 4, is an example of a discrete random variable. Discrete because when I look at the set, I can count them. 1, 2, 3, 4. There are 5 numbers in this set. They're countable, so it's discrete. Okay? Now, if it turns out that, not for flipping coins, obviously, but if I had, say, 0, 1, so 0.5, 1, 1.52, 2.53, that's also still countable, right? So I can say that that's a discrete random variable as well. So it's not about the nature of the numbers that are in the set, but the fact that they are countable. You can count them and finish counting them. Okay? So it's contained. The opposite of discrete is continuous. And the usually what you're looking for is that they are measurements. I'm not saying that's every single possibility, but I'm saying that is the most common one. Continuous is not countable. But it may be limited, but it's not countable. Yep. I'm getting there with that one because the continuous is that's a bit tricky. Can take on any value in an interval. Do you remember what interval notation means? From a number to a number. So the most common ones, I'll put it on slide 12 so it's not too squishy. So the most common ones are height, weight, time. So there are 3 examples. So, someone might be 1.8 meters tall and someone might be 1.9 meters tall, but then there might be someone who's 1.85 meters tall. And there might be someone who's 1.825 meters tall. And there might be someone who's 1.8246 meters tall. So it's continuous. So an example, this is just a mathematical example. Don't write it down. I'm just trying to give you a sense. If I said that the random variable could take on anything between 1 and 10, including 1 and 10, then there's no way of counting that. I mean, you can count the whole number bit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but for every number that you think of, then there's going to be another number that's half of that number. So between 1 and 10 is 5. Between 1 and 5 is 2 3/4. Between 2 3/4 and 5 is 4 1/5, etc. I was just making those numbers up a bit, but you get the idea. You can always find something in between kind of thing. And so it's continuous rather than being discrete. You can't count every single number between 1 and 10 unless they were specifically whole numbers. All good with that? Okay, so we've got this idea of we've got a sample space which we can just list out in its entirety. The second idea is then we can use a random variable to denote all the kind of broadly different outcomes, but you have to focus it on something. So for our flipped coins, we focused on heads, and then we said, well, if we're focusing on heads, what are the broad outcomes of that? Well, no heads, 1 heads, 2 heads, 3 heads, or 4 heads are the broad outcomes. Okay, then we can take that particular set of outcomes and we can write it as a probability distribution table. So there's your heading, probability distribution table. I'll give you a moment to write down the table and then we'll fill it in. So in a probability distribution table, we basically work out all the possible, because it's discrete, The top column ends up being the different discrete possibilities, and then we work out the probabilities underneath. So looking at that notation there, you can see I've got the probability of big X equals little x. So big X, remember, is kind of like any of those possibilities, 0, 1, 2, 3, or 4. So little x is specifically one of those possibilities. Okay, so little x will take on the values. I'll do it in a different color so you can see it. 0, 1, 2, 3, 4. I've got an extra column there. Oh well, doesn't matter. Sorry about that. The probability of x equaling little x is now saying, well, how can I get, what's the probability of getting no heads? Well, there was one way of getting no heads, and so that would be 1 in 16, because there were 16 outcomes in total. What's the probability of x equaling 1? Well, the probability of x equaling 1 is 4 ways out of 16, which you could write as 1 over 4. What's the probability of x equaling 2? In other words, what's the probability of getting 2 heads out of the 4? Well, there were 6 ways of getting that, so 6 in 16, which is equal to 3/8. I'm writing both fractions down in this box because to keep the notes clear. But if you were drawing them yourselves, you could just write down the simplified fraction. And then 3 heads would be 4 in 16 again, which would be 1 and 4. And 4 heads would be 1 in 16 again. So that becomes our probability distribution table. These are the probabilities, 0, 1, 2, 3, 4 heads, and this is how the probability is distributed amongst those particular outcomes. So you've got a quarter of a chance of getting 3 heads and so on. This is the distribution. Questions? Okay. We can draw it as a graph. So for 0, we had 1 in 16. So you can see I've got 1/8 here in my graph. So I'm going to split that in half and put a dot here for 0. For 1, I've got a probability of 1/4. So that's going to be all the way up here at 2/8. For 2, I've got 3/8. For 3, I've gone back down to 1/4 or 2/8. And for 4, I've got 1/8. Not all distributions are as neat as this, but this binomial distribution is as neat as that. That's how I would draw it. Your textbook puts lines in there, but it's up to you whether you do that or not. This is how your textbook has it. Your textbook also puts the coordinates at the top as well, which is not a bad idea, but for the sake of time, I won't. But yeah, if you look at your textbook, it's not the same example, but it does have the coordinates above the dot. And that's basically it as a graph. It's literally just a graph. So you can see that what I've got here is probability x equals x is our probability function. Our probability function. So our graph is x against the probabilities of x. That's how our function is denoted. Input x, output the probability distribution. X is input, the probability is output. We can't join those lines up because it is not continuous probability. This is not a continuous variable. It's a discrete variable, which means we can only plot points. We can't join those dots up because it's not continuous. Finally, anyone remember what that notation means? It's okay if you don't. Probably going back to year 10 maths for this. That symbol means sum. So I'm saying if I sum all across the x variables here, the probabilities of x equals x, what value should I get? This is a check of understanding. So sum means these ones, these ones here are added up. If I add up these probabilities here, what value should I get? Well done, Shaker. 1. Always. If your probability distribution table does not add up to 1, it means you've stuffed up somewhere and you should fix it. Right, I'm going to try and conclude in the next couple of minutes so that you can at least get a little bit of practice in. Okay, next bit.